right, here we go. This is a helpful video for your flipped assignment. Let's get started. A resistor of resistance R is connected to a fully charged cell of negligible internal resistance. A constant power P is dissipated in the resistor and the cell discharges in time t. Now, an identical cell is connected in series with two identical resistors, each of resistance R. What is the power dissipated in each resistor and the time taken to discharge the cell? So we're comparing two circuits here. The first circuit has a single resistor connected to a battery or a cell. The second circuit has two resistors in series connected to an identical cell. So resistors, you can think of them like hurdles or checkpoints to the flow. They slow down the current, as we can see in the simulation. So you should expect that the time taken to discharge the battery or the cell should increase. If you have more hurdles in a line, the time taken to drain the battery increases. So I'm going to get rid of two answer choices that show that the time decreases for the second circuit. And that means I'm left between two choices. I need to now determine what is the power dissipated in each of the resistors in circuit 2. So power, one of the equations for power is voltage squared over R. So the power dissipated by a resistor is the voltage lost across that resistor squared divided by its resistance value. When we have two resistors in series, remember they split the voltage, especially if they're identical. So they're each going to drop half of the voltage of the total voltage. So the voltage is lost across resistors, some in series, which means that the power dissipated is the voltage lost. This is the power dissipated across a single resistor in this series setup divided by R. You should be able to simplify that and get the right answer. Okay. Question 2, in an experiment to determine the resistivity of a material, a student measures the resistance of several wires made from the pure material. The wires have the same length but different diameters. Which quantities should the student plot on the x-axis and the y-axis of a graph to obtain a straight line? So a straight line graph has the general form y equals m times x. You typically plot the dependent variable on the vertical axis versus your independent variable on the x. The independent variable is what you can change. So they tell me this experiment involved resistivity, and in topic 5.2 there's an equation. Resistivity, rho, is equal to R, which is resistance, times cross-sectional area divided by L, the length of the wire. Okay, so they are manipulating the diameters, and by changing the diameter of the wire, if we imagine the wire has a circular cross-sectional area, the area of a circle is pi r squared. And the radius is diameter divided by 2, so the area can be thought of as pi diameter divided by 2 squared. So that's my sub out for the area divided by L. Now if you change the diameter of the wire, you are changing the resistance of the wire. So I can divide both sides by R. Pi, 4, L are constants in this case. They're not going to change. So based on what I've derived for you, you should be able to get the right answer. Question 3, a cell of EMF 6 volts and negligible internal resistance is connected to 3 resistors as shown. The resistors have resistance of 3 ohms and 6 ohms as shown. So the 3 ohm resistor is directly connected to the battery, and it will receive the entire current drawn from the cell. It gets all of it. And then we have 2 6 ohm resistors in parallel. First thing you'll do is, you'll simplify. You'll find the equivalent resistance of the resistors in parallel. Remember, it's 1 over Req is equal to 1 over 6 plus 1 over 6. Sum those and invert to get the equivalent resistance, and then combine the two resistance values to get the total resistance in the circuit. Total current is equal to the current through resistor X, and I sub X should be equal to the total voltage supplied by the cell, voltage of the cell, or the epsilon, the electromotive force, divided by total resistance. So that should get you the right answer for question 3. Question 4, a circuit consists of a cell of electromotive force, that's a voltage of 6.0 volts, and negligible internal resistance connected to 2 resistors of 4 ohms. So these are in parallel with each other. Okay, the ammeter has a resistance equal to 1 ohm, so be careful. This is not an ideal ammeter. This has a resistance of 1 ohm. It's connected in series to 2 resistors which are in parallel. So again, determine what the total resistance is in the cell is starting here. Figure out what the equivalent resistance of these parallel resistors. Add that equivalent resistance to the resistance of the ammeter. That gives you the total resistance in the circuit. Now, total resistance in the circuit. Ammeter has resistance equal to 1 and the voltmeter is ideal. What are the readings of the ammeter and voltmeter? Ammeter should be easy. You have the ammeter reading is the total current in the circuit, and that should be equal to the voltage supplied by the battery, or the EMF of the battery, divided by the R total, the total resistance in the circuit itself. Now, the voltmeter is going to measure the potential dropped across one of the 4 ohm resistors, but really the voltage lost across each of the 4 ohm resistors should be the same. But be careful, okay? These 4 ohm resistors, they're in parallel with each other, but they're in series with a 1 ohm resistor. So some voltage is dropped here, some voltage drop across the ammeter, and the remaining voltage is dropped across, lost across one of the two, each of the 2 4 ohm resistors, but they will have an equivalent voltage dropped across. The sum of the voltage lost across one of the 4 ohm resistors plus the ammeter should sum to equal 6 volts total. Current splits here, current splits here. So be careful, and if you need to, build this circuit in PhET and get the values just to prove it to yourself. Question 5. A filament lamp and a semiconducting diode have the voltage current characteristics shown and are connected in parallel. Okay. What is the resistance of the lamp and the resistance of the diode when the current in each device is 2 amperes? So this is a voltage versus current graph. V divided by I equals R. So the slope of this graph at some point, at any point, will equal the resistance of the respective lamps and diodes. But what we're looking at is this point here where they cross. So rather than just talk about the slope, what you can do, if you just take voltage divided by the current at this instant, it will tell you the resistance at this instant. They happen to be the same. All right, question number 6. The diagram shows an electric circuit containing a potentiometer of maximum resistance R. Here we go. The potentiometer is connected in series with a resistor also of resistance R. The electromotive force of the battery is 6 volts and its internal resistance is negligible. The slider on the potentiometer is moved from P1 up to P2. As this potentiometer is moving up, it's increasing the resistance experienced by the voltmeter. So if the voltmeter is all the way right here at position 1, it doesn't have a current, there's no voltage reading. I'm sorry, there's a maximum voltage reading, excuse me. Which way does current flow? Current's flowing this way, out of the positive terminal. Oh, yeah, no, sorry, there's no voltage, no voltage reading because the voltmeter is not in contact with the resistor. But as you slide from P1 to P2, the voltmeter starts reading a larger potential drop. As the resistance is increasing, as you're increasing the length along this resistor, you're measuring a larger voltage drop. Which of the graphs shows the variation of the voltmeter V with the slider distance D? So we should be seeing an increase in the voltage. So get rid of answer choice D because it's nonsensical. And in this case, it should be exactly 0 because, or at the start when it's in P1 because it's not reading across the resistor at that time, or when it's at position 1. And then it's in this resistor is in series with a second resistor, so there's no way it can experience the full 6 volts of potential difference. It's going to have to split the potential between it's going to have to split the voltage drop with this resistor up here. So based on that, you should be able to get the right answer choice. Question 7, a lamp is connected to an electric cell and it lights at its working voltage. The lamp is then connected to the same cell in a circuit with an ideal ammeter and an ideal voltmeter. That means that the ideal ammeter has no resistance, the ideal voltmeter has an infinite resistance, no R, infinite R. This keeps any current from being drawn out of the circuit into the voltmeter, and this prevents the loss of any voltage across the ammeter. But in truth, that's not how it is. Which circuit allows the lamp to light at the original brightness? And please note this should be connected. So what you can do, you can, if you would like to, build this in FET, but honestly, you shouldn't have to. Ammeters get wired in series, voltmeters get wired in parallel. Okay, a voltmeter resistance 50 kiloohms is used to measure the electric potential difference in a circuit as shown. The cell has an electromotive force of 5 volts and a negligible internal resistance. What is the reading on the voltmeter? Should be able to do this. You will calculate the total current in the circuit. The voltage dropped across this 50 kiloohm resistor should be equal to its current times the resistance. So the total current in the circuit times the resistor of this single resistor will equal the voltage dropped across it. And to get the total current, I total equals V supplied by the battery divided by the R total resistance of the series, and then the voltage across the 50k ohm will be equal to I total times 50 kiloohms. Very quick. Remember, resistance is proportional to length and inversely proportional to the cross-sectional area. Number 10, this is easy, you should be able to answer this. Number 11, energy dissipated in the resistor in time t. Remember, inner power is equal to energy over time. So energy dissipated should be equal to an expression for power times time. That's why you see all these time terms. Just make sure you have the correct equation for power here. And number 12, two resistors of resistance R1 and R2 are connected in series with a cell of EMF epsilon, that's the same thing as voltage, and negligible internal resistance. Which expression gives the potential difference across the resistor of resistance R1? Again, to get the voltage dropped or the potential difference across this first resistor, you need to first figure out the total current flowing through it. That's the current of the circuit. I total equals V total, or epsilon of the battery, divided by R total. Once you have an expression for I total, the voltage across R1 should be equal to the resistance of R1 times I total. All right, if you need any assistance, just send me a message in Teams. Thanks for watching, and study well.